The first blast of thunder on the horizon was not weather, but the distant announcement of a new era in artillery. In the smoke and sand of island battles across the Pacific, American ordnance officers and gunners began to test something that would change the calculus of close-range bombardment. Extremely high G-rated fuses designed to arm and detonate shells in the thick tangles of jungle and within ships' superstructures. Against entrenched defenders and fortified positions, the old methods, drop, penetrate, and then explode, were unreliable when enemies sheltered under flimsy overhead cover or within layered bunkers. A reliable airburst or precisely timed detonation promised to make every round count in ways that simple massed fire could not. At the heart of the change was a rethinking of what a fuse needed to do and to survive. Designers faced the brutal physics of artillery launch. Acceleration measured in tens of thousands of gravities during firing, a shock that could pulverize delicate components or render inertia-based mechanisms useless. Meeting that challenge required materials, tolerances, and mechanisms that were almost absurdly robust. Engineers borrowed approaches from aviation and industry, heat-treated alloys, precision machining, and shock-mounting techniques. To keep sensitive parts intact through the initial concussion, production had to move from theory to repeatable practice, which meant industrial processes, quality control, and standardized testing became as important as the original idea. This change had tactical and psychological consequences. When artillery could be trusted to fragment within covered positions or across the decks of enemy ships, commanders adjusted their tactics. They could order closer suppression, rely on barrages to neutralize known strong points, and integrate artillery more confidently with infantry advances. On the receiving end, defenders who had learned to shelter in lee or behind flimsy cover discovered that those halting tactics no longer guaranteed safety. The effectiveness of indirect fire became not just a measure of explosive power, but of engineering discipline and logistical reach. But technology never arrives in a vacuum. The organizational inertia of military procurement, the limits of industrial capacity, and simple human conservatism meant that such fuses did not spread overnight. American forces, with industrial and logistical advantages, were uniquely positioned to trial, refine, and then mass-produce ruggedized detonators. Training gunners to understand new capabilities and commanders to use them effectively took time and discipline. Units that moved faster in adopting these advances tended to show disproportionate results on the campaign map, but adoption required more than supply. It demanded doctrinal embrace and the willingness of leaders to gamble on unfamiliar tools. The human stories around these engineering advances are revealing. Ordnance officers, often unsung, spent months in workshops and testing ranges, iterating through designs and surviving failures that sometimes destroyed prototypes in dramatic fashion. Men in uniform learned to trust a click and a pin as much as a sighting instrument. The consequences for frontline troops were visceral. Survivors' accounts from assaulting companies frequently mention the change in the quality of supporting fire as a turning point in operations, a shift from uncertain suppression to reliable shaping of the battlefield. Engineers and technicians who once worked in comparative anonymity found their work measured in minutes and lives saved, or lost, on assault timetables. That human element was not only technical competence but the ability to communicate, to teach, and to instill confidence under pressure. Even in that era's moral ecosystem, innovations were framed as necessary responses to a brutal conflict. The narrative framing used by commanders and later historians tended to emphasize efficiency and necessity. That more reliable detonation saved lives overall by shortening engagements, while sidelining the raw human cost inflicted in a more lethal, direct way. Such narratives make uncomfortable reading now, but they reflect how military organizations make trade-offs between force protection and lethal effect when faced with brutal operational realities. The story of 20,000 G-rated survivability for fuses is as much about cultural adaptation as it is about metallurgy. Alongside engineering tolerance, maintenance doctrine evolved. Crews learned inspection routines, handling precautions, and storage measures that preserved reliability in the field. What worked in a temperate factory did not always survive salt air, tropical humidity, or the grime of forward supply dumps. Adaptations were practical and often improvised. Desiccants slipped into crates, modified packing practices, or new cleaning regimens for tiny moving parts. Training manuals grew longer, field experience shortened them again, reducing complex procedures to critical checks and habits that could be executed under stress. Those procedural lessons were crucial because in combat time is scarce and errors are costly. Soldiers and engineers traded lessons in cramped briefing rooms, where diagrams and blunt language conveyed realities that textbooks rarely captured. The mechanics of a 20,000 G Rated fuse sound like something from science fiction, but the reality lies in pragmatic engineering decisions that pieced together into something startlingly effective. Designers minimized moving parts and emphasized geometries that distributed stress rather than concentrating it. Cylindrical symmetry, tapered surfaces, and shock-absorbent seats for sensitive elements made it possible for components to survive the brutal launch environment. Where prior fuses had relied on delicate springs or fragile percussion caps, these newer units used stiffened members, redundant firing paths, and molecularly stable materials to ensure consistent behavior. Every change demanded rigorous testing. Ordnance labs subjected prototypes to centrifuge trials, shock testing rigs, and field firings that were observed and instrumented for microseconds of performance data. Failures were instructive. Sometimes the casing would flex in ways that transmitted damaging loads. Other times tiny burrs in machining would create stress risers that produced catastrophic snaps. Each failure informed small manufacturing tolerances that became crucial. 1/10 of a millimeter too large could mean the difference between reliable detonation and a dud that failed at the worst possible moment. The end product was not merely a design but a set of manufacturing and quality control standards that turned fragile concepts into robust commodities. The battlefield impact extended beyond simple lethality ratios. With improved fuses, artillery barrages could be calibrated to create different lethality profiles. Immediate fragmentation, delayed buried charges, or airburst effects that maximized shrapnel spread over a broad area. The difference between a ground burst and an airburst is tactical poetry. A ground burst concentrates force downward and into earthworks, while an airburst scatters fragments in an envelope that sweeps across entrenched positions and clears overhead cover. That choice shaped how commanders choreographed barrages to shape enemy behavior, to create funnels and kill zones, or to make certain routes impassable without exposing attacking troops to prohibitive risk. Logistics and doctrine had to catch up. Artillery units learned new fusing tables and firing techniques. Fire direction centers updated their calculations, integrating fuse settings into the timing and sequence of barrages. As doctrine evolved, combined arms operations incorporated timed detonations to shape enemy behavior, channeling defenders into predictable locations or flushing them from cover at predetermined instants. In practice, this coordination required discipline, reliable communications, and a level of rehearsal that transformed artillery from a blunt instrument into a precise shaping tool. The psychological effect cannot be overstated. Troops learning that bombs would reliably airburst over their positions developed a new kind of dread. Shelters and revetments that had been learned through bitter experience to offer protection were suddenly suspect, eroding the small certainties that soldiers rely on in combat. Commanders capitalized on this by adjusting assault timetables and using artillery as a tool not just of destruction but of manipulation, to force movement, to create gaps, and to synchronize infantry maneuvers with predictable suppression windows. That manipulation worked because the technology delivered predictable results. Unpredictability is the real enemy of coordinated action. Yet for all the technical clarity, there were operational limitations. Environment matters, humidity, salt air, sand, and jungle rot presented unique maintenance challenges that could degrade even the best-built mechanisms. Supply lines under enemy interdiction could not always bring forward the newer munitions in sufficient quantities, leaving some units to choose between older, less reliable shells and cutting-edge ordnance. Moreover, the enemy learned too, they adapted. Countermeasures included deeper burials, reinforced overhead protection, and revised defensive postures that traded immediate exposure for later mobility. Intelligence and counter-intelligence efforts sought to track where new munitions were used and how defenders responded, creating a dynamic interplay between offense and defense that never rested. In theater, ordnance depots and supply officers became pivotal nodes. Getting the right fuse to the right battery at the right time could be decisive. Field reports often read like engineering lab notes crossed with combat diaries, where observations translated directly into modified parts lists and altered assembly steps. Every change rippled outward. A tweak in fuse design could require new handling procedures, revised safety protocols, and updated user guides for frontline crews. Soldiers and engineers continued to trade lessons in cramped spaces, where the pace of change demanded rapid learning and even faster unlearning of old assumptions. The legacy of those innovations extends into doctrinal lessons and industrial history in ways that outlived the immediate conflict. Engineers who solved extreme G survivability problems crossed over into post-war industries. Materials science, precision machining, and quality control techniques found civilian applications in aviation, automotive safety, and even in the nascent electronics sector. Military procurement that had once been described as plotting became, in certain domains, more iterative, with rapid prototyping ideas slowly seeping into practice as lessons from the front shaped peacetime industry. On the human level, the stories of adaptation and improvisation endure. Veterans who lived through the pace of change often recall how new equipment forced reassessment of long-held survival instincts. Platoons that had relied on certain terrain features for safety had to relearn what cover meant. That relearning was costly because mistakes were fatal, and doctrine often evolves through harsh, tragic examples rather than gentle instruction. Yet the same veterans also speak of the grim clarity that reliable equipment provided in the moment. When support behaved as expected, commanders could plan with confidence and soldiers could act without second-guessing the tools at their disposal. Historical analysis must be careful about causal claims. Technology is rarely a single decisive factor in a campaign. Logistics, leadership, morale, and luck are intertwined variables. However, when a technological improvement so directly alters the interaction between offense and defense, its effects ripple through tactical, operational, and strategic layers. High G-rated fuses changed the equations for close-range artillery. They altered choices and forced adaptation at multiple levels, from the individual gun crew that set a fuse on the eve of battle to the theater commander who integrated new capability into campaign plans. That alteration is instructive because it illustrates how engineering constraints and battlefield realities co-evolve. There are ethical and reflective questions that follow. Increased lethality forces societies to confront how they wage war and what means are acceptable, even in existential conflicts. Historians must weigh the tactical advantages against human costs, and remember that behind technical descriptions and procurement records lie lives altered and ended. The narrative of engineering triumph must be balanced with empathy for those on whom the technology was used. It is a sobering consideration that every improvement in effectiveness translated into a corresponding increase in suffering for some human beings, and that such trade-offs were rarely, if ever, purely technical decisions. Finally, in recounting technological surprises such as these, we should resist simplistic valorization. Instead, a nuanced narrative recognizes both ingenuity and consequence. The story of 20,000 G-rated fuses turning artillery into a meat grinder for defenders is not merely a tale of engineering excellence. It is a case study in how innovation intersects with doctrine, logistics, and human cost. That intersection remains relevant today wherever rapid technical change meets entrenched practice, because the lessons are perennial. Effective innovation requires not just good ideas and good metallurgy, but the institutional capacity to test, to train, and to reckon honestly with the consequences of what those ideas make possible. Soldiers and engineers will always tell similar stories about the dance between risk and reward, and historians will continue to untangle the threads that connect a small mechanical improvement to outcomes that shape lives and nations. Those threads matter because they remind us that human choices are woven into every mechanism, and that progress without reflection can be as dangerous as it is dazzling. Soldiers and engineers traded lessons in cramped briefing rooms where diagrams and blunt language conveyed realities that textbooks rarely captured.